Hi everybody, welcome back to Science for today. We have the next 2 weeks of assignments and then we're almost done, so reason for celebration, right? Today we're going to be talking about what is an acid and what is a base. So the first thing you need to know is that acids and bases are found in our own houses. And as you can see, we can have acids in everything from our stomach to the things we drink. So inside batteries, milk, coffee. We can even have it in our soap, in our bleach, in our cleaners, and baking soda. So things that we cook with as well. So just so you know, acids and bases are all around us, and they happen in our everyday lives, and we carry them around in our body. In fact, our blood is slightly acidic. It falls into the 5-ish range, excuse me. Uh, when we talk about, well, what is the pH scale of our acids and bases and of these household items, you'll notice that there are different colors associated with it. So you're seeing the pH color as if you would see it in an indicator. So acidic pH ranges from 0 to up to 7, and then basic pH ranges from just above 7 to up to 14. So the acidic ranges are in the reds and yellows, and the basic ranges are in the blues and purples, with 7 neutral being right in the middle. And so you get a good idea of what some of that looks like as well. Sometimes we have to be able to define what is an acid and what is a base. And so we have two ways of defining that. The first way is called the Arrhenius definition. It's the oldest way we have. And that definition is based on whether or not an acid donates a hydrogen. In other words, the acid has a hydrogen to give away in water, or a base donates a hydroxide. And while that did work, at least in the beginning of things, we have a broader range of what those things are now. So we have to be able to look at it in a slightly more complex manner. So instead, we mostly use this definition, which is called Bronsted-Lowry definition, and it says that an acid donates a proton in water, whereas a base accepts a proton in water. And so that's a little bit more broad-based for us. So if we define a base as anything that can accept a proton in water, in other words, it has to have a lone pair of electrons, then more examples of bases can be used. So for instance, we will have an acid, and you might notice that we have an acid that is defined here as water. And you might notice that, and you might wonder, well, what is going on with that? Well, water in relationship to, or in relatively speaking to the base, the ammonium, the water is more acidic. So in this case, water is going to act as an acid. As you can see, it's going to give away a hydrogen and become the hydroxide ion. So we call this an acid conjugate base pair. Now, what about the base? Well, the base, as we've defined already, accepts the proton in water. So the base becomes this conjugate acid. That's new terminology for us. And that means the ammonia and the ammonium ion then are our conjugate acid and base pair. Now you might be going, where does the H's come from? I don't understand. So let's go take a look at this in a little bit more depth. Take a look with me here. When we're talking about Bronsted-Lowry reactions, that means what we mainly want to pay attention to is the transfer of a hydrogen ion. And so we're calling it a proton because protons are hydrogen ions. They consist of one proton. Hydrogen has only one proton. Okay, so let's take a look at how this works here. In this case, our acid is giving away its hydrogen to the base. And you might notice right in the middle here that we have a double-sided arrow. That means on the product side, we also are having a reverse reaction happen. In this case, we have the acid giving away its hydrogen to the base. But let's stop and identify a couple of things here. The first thing I want you to notice is that when the acid gives away its hydrogen, what's left over is something we're calling the base. So this is, as we referred to last time, the conjugate acid and base pair. We can do the same thing with the base. So in this case, water was acting as the base because water is more basic than hydrochloric acid. So water is receiving the hydrogen. So water receives the hydrogen, and then water becomes water becomes an acid because it has more. So it has more hydrogen. So we have another conjugate acid and base pair. And we can go make those pairing things for a couple of other things. In this case, we have a base. It is receiving the hydrogen, and that base is becoming an acid because it gets the hydrogen. So that is our conjugate acid and base pair. And then we have our acid losing a hydrogen. That's our acid losing the hydrogen, and what's left over is the base. So there is another conjugate acid and base pair. Let's try that one more time with one that you can't see all the way. Here we have our acid because it's losing a hydrogen. Now, which one would you think that it would become? Well, when this loses a hydrogen, it's losing one of its H's and a positive charge. So it becomes HSO4 1-. That's what's left over. So that's our first conjugate acid and base pair. So where is our other one? In this case, water is acting as the base because it's receiving the hydrogen. And then when water receives the hydrogen, it becomes this special thing. It looks like water, but it's different because it has one extra hydrogen and a positive charge. And we call this the hydronium ion. Okay, you are going to move on to the next part where you are going to try this all by yourself, and I want you to give it a try. Okay, after you've tried that, you make sure you turn that page in so I can see you having given that a try. We also need to define what is actually happening in terms of how strong are these acids. Are they going to eat through our skin? And so you need to understand that we have two different terminologies. When we are talking about a concentration of an acid, we are literally talking about an acid that has the power to eat through clothing and skin and so forth. However, when we talk about the strength of an acid, we are saying something completely different. We are asking how much does it separate into ions? In other words, how much does it dissociate? So these are two different things. Acids can all be dangerous if they have enough concentration. However, not all acids are considered strong acids in that they all don't dissociate into their ions. Let's take a look at what we mean by that. When they dissociate into their ions, it changes their pH. When an acid is fully dissociated, it is a strong acid. So you'll see the pH down here in the 1 to 2 range. When an acid is not fully dissociated, it is a weaker acid. So you'll see the pHs in the 5s and 6s. The same thing is true of the bases. A weak base has a pH in the 9 to 10 range, whereas a strong base has a pH more in the 13 to 14 range. So what does that look like? We don't really understand until we see a picture. So let's take a look at a strong acid. Inside the beaker, the strong acid has all of its ions dissociated. You can see that in the graph to the right, where all the ions are dissociated apart into H1 pluses and A1 minuses as our example. However, if you compare that to the weak acid, then you'll notice that most of the ions are staying together and not dissociating. In fact, only a small amount of the ions of a weak acid or base dissociate. So that's going to be our main difference between where we designate something as a strong acid or a weak acid. All right, you are going to be doing an explore laboratory where you go see if you can work through a laboratory where you play with a simulation, and you are going to record some properties, and then you're going to summarize what you have seen. You need to know, put your concerns at rest, that if you make any mistakes here, this is not going to be the end of the world. I am looking for, did you do the work? Did you try this out? Did you investigate? So please go enjoy your investigation and make sure that you turn both um, your acid, conjugate acid base page, defining acids and bases, and turn in your virtual laboratory explore lab. Thank you guys. Have a good week.